Good morning, good afternoon, and good evening, everyone. So today we're going to be talking about projectile motion. So this is one of those math topics I'm particularly excited about. So just a brief recap of what we discussed in the last video. So we started off reviewing the ideas of velocity, speed, and acceleration in terms of vectors. And so we were able to go through some exercises here of basically finding the velocity, acceleration, and speed. So that's pretty much it. So we were able to somehow get an idea or get the gist of how these are seen in 3D vectors. And we were able to use derivatives and integrals to calculate some of these vectors. Um, and we also came across a physics concept here, which was about finding the force of an object using its mass and acceleration. And we were able to discover this idea of centripetal force, which is the idea of the force keeping an object moving along its circular path. And that force points towards the origin. So it's kind of like gravity, if you imagine. If this circle, I'm assuming this is a unit circle, but this blue circle is kind of like Earth, where us humans were being gravitated towards it. So that's how we're able to um, maintain here. So we're able to stay here. But yeah, enough of that. Let's talk about projectile motion. So let's do an example here. So surprisingly, the textbook starts off with an example. Um, so it's saying that a projectile is fired um, with an angle of elevation. So it's fired at a particular angle. We're calling it alpha. And the initial velocity, let's say it's v naught. Okay, here we assume that air resistance is negligible. Negligible. What does that mean? It means like it doesn't exist, right? Oh, it's insignificant, so it's not important. So we're not considering, okay, so we're not considering air resistance here, but we're only considering a force. And it's the only outside force. It's the only external force, which is gravitational force. So that's what we're considering in this projectile motion. And so we want to find our task here is we want to find position vector. We're going to call it R of t of the projectile. So here we're only considering there's gravity. And yeah, there's no like other air, there's no wind, there's no nothing, there's no none of those. Um, so that's the first task is we find R of t. The other task is we're asking what value of alpha maximizes So something about optimization when we hear the word maximizes, maybe. Maximizes the range. What do I mean by that? Well, I mean the horizontal distance traveled. So how can we make the most of that horizontal distance? Because obviously, if we put in more speed and if we fire it maybe at a very, very optimal angle, we'll probably get farther, right? Our projectile will probably get farther. So we'll see. First, I'm gonna screenshot a particular figure showing the fundamental idea of projectile motion. Oh, where did it go? Went here. Where did you go? Oh, there you are. I was like, wait, the figure's gone. What? Okay, so here's the figure. Okay. And so how do we approach this problem? So first we want to find RFT. So I guess the first thing we can do is set up the axis or the axes so that the projectile starts at the origin. So we kind of already did it here. We have our y-axis, we have our x-axis, right? And the projectile will start at the origin. And since the force due to gravity or gravitational force acts downward, right? So we're going to have to consider this Newton's second law, which is that mass times acceleration is force. And since it's acting downwards, then it's going to be negative of that gravitational force in J. So this is an IJK, right? We're saying G. So where in the world did G come from? It's actually just the absolute value of A. And that is approximately negative 9.8 meters per second squared. So that's gravity. And the J, well, because we have a vector going down, right? We'll call it the G vector. And this G vector is actually just 0, negative 9.8 into D, right? Because again, it's going down. Yeah. So that's my vector. Okay. And so from here, if G is the absolute value of A, well, we can say that A is equal to negative G, J, right? Mhm. So the distance of A, or the magnitude of A, is G. So if we get A instead, yeah, then we have negative G. This is a physics thing. So if any of you could explain it better, please do. Okay. And from here, we can say that uh, since we know that our velocity, or the derivative of our velocity vector, is basically A, which is our acceleration, then we actually have this thing. We have our v of t is equal to negative g t j plus some constancy, right? Okay. And from there, Okay, let's define what C is. What is C? C is V naught, right? That's V naught. That's the initial velocity launched, right? And then we're subtracting some gravity and we're parameterizing it. That's why we have a time. Because we want to find which it's, yeah. And basically here we just took the antiderivative of this thing in terms of t. And so we get something, we get t here. We leave this negative g alone because that's constant. And we add some constant c. So we actually integrate a here to get our v of t function, our velocity vector function. And then from there, now we'll be able to find so from here, we can now find our position vector, or r of t, which is actually just r prime of t. So if we take the derivative of that position vector, it's just the velocity vector, which is this thing, negative g tj, plus my initial velocity. And so we integrate that again. And we should get negative 1/2 gt squared j plus t v naught. So v naught here is a constant, right? So we multiply it with a t. And then plus another constant, which we'll just call d. Then we can define this. D is equal to r of 0. And that initial, at time 0, I'm assuming t is time. Our parameter t is time. At time 0, well, our position is 0 at the origin, right? And so position vector, now we have our final answer. Position vector is r of t. We put our negative 1/2 g t squared j plus v naught. That's it. Or plus t v naught. My bad. Okay. And that's actually one of the important things you're gonna look for. Okay. If we write the absolute value of our initial velocity to be, whoa, okay, that's a different looking v naught. What's this then? Means it's a vector. So here we actually say this is a vector. Just to not be confused. Okay, let me edit. But this is a vector, right? Okay, what else are we missing? So if that vector is equal to the initial velocity, the actual initial velocity, or we call it the, sure, initial speed or velocity. Let's call it initial speed to be more precise. So that's the initial speed of the projectile. And what can we say about it? Then we say that our vector, our initial vector velocity is the initial velocity cosine alpha at I plus the initial velocity cosine alpha, no, not cosine, sine at alpha j, right? So these are positions. These are positions. And from here, we now have an equation 3, a modified equation 3. So here we say r of t is now v naught cosine alpha to the t I, right? And this is added to v naught sine alpha t. And then I subtract 1/2 gt. I square that thing. J. Okay. So here now I have my I and as well as my J. And so from there I have parametric equations that I can work with. So from there, the parametric equations of the trajectory are this one. X is equal to our cosine part times c. These are parametric, and y is our sine part in terms of t as well, minus 1/2 gt squared, which I did derive here in one of my Angry Birds videos. I did theta instead of alpha, but it's totally fine. Yeah, and then we were able to derive this thing. So that's horizontal and vertical motion. Okay, where was I? Week 4, I believe. Yeah. And so from there, the horizontal distance, let me just do this. The horizontal distance, d, is the value of x when y is 0. And setting y equals 0, we obtain t equals 0. Okay, let me derive the horizontal distance. So here we're saying the horizontal distance, which we'll just call d, is the value of x, specifically when y is 0, right? And when we set y to 0, what t do we obtain? So setting y equal to 0, we obtain 2t values here. So let's actually check how it works. Okay, we have v naught sine alpha times c minus 1/2 g t squared, right? And from here, I can divide the t to both sides. So I get 0 v naught sine alpha minus 1/2 g t. Okay, now what can I do? I can modify this a bit, maybe put like g over 2 times t maybe. I could put v naught sine a to the other side. So that would give me, or actually this one, I could put this to the other side. G half t equals v naught sine alpha. And then from there, I could just multiply 2 over g to both sides. So that would give me t 2 over g times v naught sine alpha. What else can I do? 2v naught. Yeah. So that's what it gives me. It gives me this value for t, but it also gives me t equals 0 from here. Because if I make these 0, I get a 0 value. So if we make y 0, we actually obtain two values of t. 0 and t equals, well, 2v naught sine alpha over g. Yeah. So we obtain these two things. What else? Oh yeah. So to make it more general, let's use the second value of t. So I'm gonna say using second value of t, well, we should get our distance, horizontal distance d, which is just equal to x, which is, so let's use our x here, v naught cosine alpha, right? And we multiply it to our t, so 2v naught sine alpha over g, right? And then from there, we can get v naught squared, because we're multiplying these two. And we also get a sine alpha cosine alpha. So we have 2 sine alpha cosine alpha. We divide that all by g. And actually, funny enough, this is a trig identity. So this is just sine to alpha. Let me rewrite that better. Sine to alpha. Oh, I did this. Let me just do that. There we go. So sine to alpha over g. So that's my x, right? This is my x in terms of its angle alpha and its initial velocity. So how can we find the maximum value? Because that's also what we're trying to find here besides r of t. We're trying to find what value of a maximize, well, not a, what value of alpha maximizes the range. So, or specifically the horizontal range. So we were able to define this. So what's the maximum value of alpha? Well, here we can clearly see that D has its maximum value when my sine of 2 alpha is equal to 1. And so from there, my alpha should be 45 degrees, right? That's the maximum. That's the maximum alpha we need in order to maximize its range. Okay, I hope that makes sense. Okay, let's look at another example here. Oh, we actually have a couple more to go through. Yeah, besides projectile motion, because projectile motion, we're just gonna use formulas basically. Okay, so let's look at one last example of projectile motion. And I'm gonna cut the video there so that we can talk about something else. Okay, so example 6. But really, this is a physics application of velocity, speed, and acceleration. That's the main topic here. Okay, so for example 6, we fired a projectile, and it has an initial speed. So here we're talking about speed. So now we put some numbers. 150 meters per second. And we're saying the angle of elevation the angle of elevation 30 degrees from position 10 meters above ground level. Okay. So we're not at I'm assuming we're not at the origin here. We're 10 meters above the ground. Okay. Where does the projectile hit the ground? So it's asking for coordinates here. So here we can make use of the formulas we made. Okay. So where does the projectile hit the ground? And at what speed? So once it hits the ground, what's the speed? Right? So let's say the origin is at the ground level. Then the initial position of the projectile is at 0, 10, right? So I think the first thing I'm gonna do here is, well, obviously we're gonna sketch a scenario, and we're gonna do it in 2D. We're gonna impose that, okay, this is the ground level. So we're saying the horizontal x-axis is the ground level. And we're saying that the position of this projectile is here. So we're gonna say 0, 10 projectile. Okay, let's see if I can write that really nicely. Okay, never mind. And so we need to actually adjust our equations for by adding to the expression y. So we need to add 10, right? And then here we just plug in what we know. So here, use parametric equations. So we're going to make use of the two that we got right here. Our x is v naught cosine alpha times t. And then our y is, well, what was it? V naught sine alpha t. minus 1/2 gt squared, right? And then from there, well, our x is going to be the same, right? Let's actually make use of our given. Our v naught, what's our v naught? Our initial velocity is 150 meters per second. So let's plug that in. What's our alpha? It starts at an angle of elevation 30 degrees. And lastly, what's our position? 10 meters above. How do we make sure to incorporate that? Well, our x value is still the same. We put 150 there. We put cosine of 30 degrees there. But here our y is different because our y starts at 10. So we add 10. Then v naught is 150 sine, I almost put alpha. I meant to put 30 degrees t. Then we subtract 1/2. Then here we incorporate gravity. So we put, pretty sure we put 9.8 here. Yeah. And then we put t squared. Can we simplify? Let's simplify. I'm going to put this down so that we can simplify everything. Okay, let's simplify my x. So my x is going to be 75 square root of 3t, right? And then my y is going to be, well, we have a 10. We add 75t, and then we subtract. So 9.8 divided by 2, 4.9 t squared. So apparently this is quadratic. This is a parabola. So that's interesting. Okay, so the question was, where does the projectile hit the ground? And with what speed? So the impact actually occurs when y is 0, right? So here I'm going to say find when projectile hits the ground. And here we're simply going to say that happens when y equals 0. So it happens when y equals 0. So we say 0 is equal to 10 plus 75 t minus 4.9 t squared. Then here we just use a quadratic formula or something else. But yeah, if we were to solve for it, we'll get t equals 75 plus square root of 5625. We add 196 over 9.8. And we should get somewhere 15.44 seconds. So that's just approximating it. Okay. And then if we approximate x, so I think that's the other question. Where does the projectile hit the ground? Oh wait, was it asking where or when? Oh, it was asking where. So approximately, if we put this to our function as our t, 15.44, well then it would approximately go 2006 meters away. Yeah. Okay, what else? So that's where and when. And that's asking with what speed. So here we find what speed. So here we just get the velocity vector, right? So we take the derivative of our position vector here. Oh shoot, do we have that? Oh yeah, we have that. It's these ones. This one and this one. So I'm pretty sure we just get the, yeah, we just get the constants here. Yeah. So if we take its derivative, well, we get 75 square root of 3 for my x. And for my y, we get 75. We add that to, we don't add it. We subtract it to 9.8. Oh, what happened here? Okay, we subtract it to 9.8. And then this just becomes t. Okay, I think that should be it. Yeah. And then it's asking for a speed. So that means we get the absolute value of my speed specifically after around 15.44 seconds. And so we just take a square root of all of that. Then here we add it to this, and we should get some value. Instead of t, I plug in 15.44. And we square that. So we're gonna get some value here. I'm not gonna compute it anymore, but it should be around 151 meters per second. So that's the speed as it's about to hit the ground, or as it hits the ground. That was the speed. Okay. Yeah, that's pretty much it for projectile motions. I hope you guys learned something, and I hope you had fun with this simple example of projectile motions. And yeah, I'll see you guys in the next one. I'm actually gonna tease it a bit, maybe. I'll just tease it a bit. So the next thing we're gonna talk about is this idea of tangential and normal components of acceleration. Yeah, so we're gonna talk about that. Okay. So basically, just to keep it short, we're going to study the motion of a particle. So one's going to be the direction of the tangent, and the other is going to be the direction of the normal. Um, so yeah, just something to keep in mind. Um, okay. Yeah, these are used for analyzing motion in a nutshell. Okay, so yeah, that's it for this video, and I'll see you guys in the next one.